Alright, welcome back. In the previous module, we work with services. We use them to control a gripper, opening and closing it instantly. That worked perfectly because the operation was fast. But now, let's think about a different situation. What if we want to move our robot arm to a new position? That's not an instant movement. It might take several seconds. If you use a service for that, the client will block and freeze until the movement is finished. We get no progress, no feedback, and no way to stop it. That, that's exactly the problem actions are designed to solve. In this module, you will learn what an action is and how it works internally. The three parts of an action is goal, feedback, and result. How to define a custom action using a .action file, how to create an action server for long-running logic, how to create an action client that receives feedback, and finally how to test action using both Python and the ROS2 CLI. Before writing any code, let's clarify the difference. A service is like asking a question and waiting silently for the answer. An action is like starting a task and staying informed while it runs. Services are best for quick commands and instant responses. Actions are best for long-running tasks, tasks that need progress update, and tasks that might need to be cancelled. An action is made of three parts: a goal, what we want to do; feedback, what's happening right now; a result, what happened at the end. Let's start by defining our own action. We want an action that moves our robot arm to a target position. So we need a goal, the target position; feedback, the current position during movement; a result, whether the movement succeeds. These definitions live in a .action file and act as a contact between the client and the server. We create an action directory inside our interface package, just like we did with services. Now let's create the action definition. The file is divided in three sections. Everything above the three lines is the goal, between the separators is the result, and the bottom is the feedback. This structure is mandatory for all ROS2 actions. Just like services, actions must be generated before we can use them. If we forget this step, Python will be able to import the action type. At this point, the action exists at the ROS2 level and is ready to be used. Now we build the action server. The server is responsible for receiving the goal, executing the long-running logic, publishing feedback while running, returning the final result. In this example, we simulate a robot arm by slowly increasing a position value over time. Here what's happened: we create an action server, the execute callback runs when a goal is received. Inside a loop, we update the current position, we publish feedback, sleep to simulate a real hardware delay. When finished, we return a result. This is exactly how a real robot controllers behave. Now let's create the action client. The client sends a goal, receives a feedback asynchronously, gets the final result when the action finishes. Unlike services, the client does not block while waiting. Notice how the client reacts to events instead of waiting. This is the key difference between actions and services. To run our nodes using ROS2 run, we must register them in setup.py. Now let's see actions in action. You will see the goal being accepted, the continuous feedback updates, a final result when the movement finishes. This is exactly what we are missing with services. You don't even need Python to test action. ROS2 provides powerful CLI tools. This is extremely useful for debugging and inspecting robot behavior in real systems. In this module, you learn why services are not suitable for long-running tasks, how actions solve that problem, how to define a custom action, how to implement an action server with feedback, how to write an action client, and how to test actions using both code and CLI. In the next module, we'll stop launching nodes manually. We will use launch files to start the entire system with a single command. This is how real ROS2 systems are deployed.